Welcome back to week 2 of SC0X Supply Chain Analytics. And this week is the first of 2 weeks where we'll talk about optimization. These are prescriptive models that tell you a solution. They're not just describing or predicting something, they're recommending a solution to a problem. And so we're going to talk about 2 types of optimization here. We're going to start with unconstrained optimization and then talk in the second lesson about constrained. So we've already laid the groundwork for unconstrained optimization, where you might have some kind of, say, a profit function, and we know from our previous lesson that that could be a function of price. So what I want to do here on my axis is this x variable is the price, and we say if you determine the price, that'll help determine the profitability. Because if I set the price too high, no one will buy it, and I won't make any money. If I set it too low, many people will take it, but I won't make any money. I'll be unprofitable. So we can describe this pretty accurately as this quadratic. And so what we want to do in this lesson is determine what is the level of P, what is my, call it P star, that gives me the optimal profitability. What price do I set to maximize my profit? So what we're doing here is finding extreme solutions of a function, either a maximum or a minimum. And in this case, we're looking for the maximum here. So looking at it, it's pretty obvious. We know it's going to be right up here, right? And we can kind of draw it out. But in real life and in the problems you'll have, it's not going to be as obvious. So we're going to need a technique. And the tool we're going to use, relies upon slope. So we'll be looking at the slope of this function at different points. So at this point, I can draw what the slope would be. And I can do this all the way up. But at some point, that slope is going to be at the top. And at the top of that extreme point, that slope will be 0. So remember that slope is simply the change in y over the change in x. So when that is equal to 0, when the slope is equal to 0, then we're at an extreme point, in this case a maximum. How will we be using this? We'll be using differential calculus. Relax, it's very easy, and I'll step you through it. But it's essentially we're going to say dy dx, at the point where that is equal to 0, that is where my optimal value will be. So this works for maximum or minimum functions. So for example, I could have something down here where I have a cost function. So my inventory cost, and that could be a function, as we'll see in later lessons, of my order size. So the quantity that I order. So this x here would be, we'll use the letter Q for quantity. And up here, it'll be the cost of my inventory. And as we'll see, this function actually looks something like this. It comes down high, then it starts going back up again. And so we'll be using the same technique, seeing how the slope changes as I move down this function. You see how it changes, and at some point, it's going to be equal to 0. And where it's equal to 0, that's the extreme, that's the optimal point to give me my extreme solution, which is a minimization in this point. It's my minimum cost. That's the order quantity I should use. So this is unconstrained optimization using all the functions we learned in the first lesson, and we're going to apply that to find extreme solutions. Now we're going to move into constrained optimization. And what we're doing here is constraining the space. And so typically, you're going to have 2 different variables here. You're going to have an x1 and an x2. And so let me give you an example of one that you'll see that's very common. Suppose I have a profit function, and my profit, we're going to say that's equal to z. Don't ask why, it's kind of common nomenclature. And that's going to be a function of 2 variables, x1 and x2. And we want to find the profit, we want to maximize that profit. So we want to maximize the profit given that there's an x1 and an x2. This could be 2 products. How much do I make of one versus the other? Because each of them have different profit margins, they have different constraints. So this is a widely used formulation. And so this function, we'll restrict ourselves to linear functions at this point. So this could be something like 3x1 plus 4x2. And that's simply saying if every unit I sell of x1, I get $3, and every unit of x2, I make $4 profit margin. I want to find the x1 and x2 that maximize that. And you can kind of see why this has to be constrained, because if not, I'd produce as many as possible. I'd be way out here. So it's going to be constrained. So let's talk about the constraints. So I have an objective function up here, and it's going to be subject to a series of constraints. And we can write these as a function, and I'm just using a g here instead of an f because I already used the f. G is a function of x1 and x2, and this is going to be less than or equal to b. Now, all that we're saying here, it's a nice compact way of saying something like this. Well, maybe x1 plus x2 has to be less than 10 because I can only make a total of 10. That's my capacity. I might have something like 2x1 plus x2 has to be less than or equal to 16 because that might be the amount of raw materials I have. And this x1 takes 2 units when x2 takes 1. So you have all these different physical constraints that you'll turn into functions, linear functions in this case. And we probably want to make sure that x1 and x2 are greater than or equal to 0. I can't make negative product. And so what are we doing here? Well, now I've got an objective function and I've got some constraints. Let's start with the constraints, and I'm going to graphically show what they mean. This is the stuff you'll learn in the second lesson. So let's take the first one. x1 is greater than 0. What does that mean? Well, that means my solution has to be somewhere on this side. x1 has to be greater than 0. So that one's done. What about this one? x2 greater than 0. Well, that's simply meaning my solution has to be up here. So I know I'm going to be somewhere up in here. So now let's go down the other constraints, and we'll show you how to do this more formally. But x1 plus x2 less than or equal to 10, I can draw that line. It's going to really be a 45-degree angle, and we know that it has to be less than that. I can either produce 0 of x2, 0 of x1 and 10 of x2, or 0 of x2 and 10 of x1, or some combination of the two. The second one is going to look something like this, and it's going to say you've got to be below that line. So what we do, we might have more constraints here, but it defines this space, and this is known as the feasible region. And so the feasible region defines the solution space of my problem. My solution has to be some combination of x1 and x2 that lies within this space. And that's a great thing. Now I'm constrained. My solution is somewhere in here. So how do I determine my solution? Well, now I want to find the profit function that is maximized, but still stays within this space. This is still a linear function, so I can actually draw that. It's going to look something like this. And as I increase the value of that profit, it's just going to move out in this direction. And at some point, it's going to bump against the constraints. And in this case, it'll come up to there. So I'm moving my profit function up until I can't move it any further, or it'll fall out of the feasible region. And this is the solution. And that's the optimal solution. I put Z star because the maximum profit, and that's going to be at x1 star, and across here, x2 star. So what are those things telling me? It's the optimal amount of x1 I should make and x2 I should make to maximize my profit. So this is the building block of optimization. We're going to start with unconstrained, move to constrained. It's the framework that we'll use and is embedded in every software system you see in supply chain management that gives you a recommendation or a solution. All right, I hope you enjoy the videos and recitations where we explain more depth these concepts. And please use the quick questions, do the practice problems. They're there for your benefit. Hopefully you'll use them to learn. All right, let's get optimizing.